Today we're going to do a calorimetry lab. You could follow along with your own materials, or you could just use the data that I provided for you. If you have a styrofoam cup, a thermometer, and hot and cold water, you could follow along and do this one yourself. All right, we went over the equation Q equals mCT. Here's a refresher of what everything means. Q is the heat, M is the mass, C is the specific of the material, and delta T is the change in temperature, the T final minus the T initial. If Q is a positive number, that means heat is flowing into the system. The surroundings are going to get cold. If Q is negative, heat is going to flow out of the system and the surroundings are going to get hot. Okay. All right, so let's start with the practice problem. How much heat is given off when 869 grams of an iron bar cools from 94 degrees to 5 degrees? Okay, so one thing we need before we get started is the heat capacity of the iron, which is C of the iron, which equals 0.444 joules per gram per degree C. And we know our equation Q equals mc delta, and we could use that to measure the heat, which is Q. All right, so the mass is given to us. The mass is equal to 869 grams, and it's cooling from 94 degrees to 5 degrees. So the delta T, which equals T final minus T initial, equals 5 degrees minus 94 degrees, which equals negative 89 degrees. Okay, so now popping that into our equation, I have Q, which equals 869 grams times 0.444 joules per gram per degree C times my minus 8 degrees C. Degrees C are going to cancel out, the grams are going to cancel out, and you're going to get a value of Q with the correct number of sig figs as minus 34,000 joules. And this is negative. That means heat is leaving the iron, it's going out. And where's it going? It's going to the system, which is everything else. It's going to the surroundings. Okay, so let me ask you a question before we do the lab. If I had 50 grams of water at 20 degrees C and added 50 grams of water at 40 degrees Celsius, what would the final temperature be? Take a second, think about it. Okay, hopefully most of you had said 30 degrees Celsius, right in the middle. I have equal amounts of water coming together. I have my cold water, 50 grams at 20 degrees Celsius, and I mix that with another 50 grams of water at 40 degrees Celsius. When I mix those two together, I'm going to get 100 grams, and it should be at 30 degrees Celsius. Calorimetry is a way of measuring this. If the numbers don't work out as easy as these do, we could actually do the math and figure out what that's going to be. All right, so let's experiment. Okay. So calorimetry, the first law of thermodynamics, says that energy can't be created or destroyed. We just convert it from one form or the other. And we also learned that heat flows from the hot object to the cold object. So the hot object gives up its heat, the cold absorbs that heat. All right, so what would happen if I added those two together? I take the energy of the hot, which is going to go out, it's going to go to the cold, and that's going to, what do they equal if I add them up? Hopefully you came up with 0, right? All the energy that the hot gives up, the cold is going to absorb. And that's pretty much the nature of calorimetry. We use this equation, hot plus the Q of the cold equals 0, to figure out the missing components of our experiment. Okay, so let's watch the experiment now. So I don't have a calorimeter at my house, but I do have a thermometer that can read in degrees Celsius, and I have a baking scale. So I'm going to turn the scale on, set to grams, and we're going to zero it. And I'm going to zero my thermos, which I'm going to use as a calorimeter. Okay, so hit the zero, and now I'm going to put some cold water, fresh from the tap, and put about a half a cup inside the calorimeter. Let's take the temperature. See where it winds up. So, as far as the mass, we have 107 grams for the cold water. And the temperature, let's see where it stops. Let's say 14.1. So the initial temperature is going to be 14.1 degrees Celsius. All right, so I have my coffee pot boiling. I'm going to use the same half cup measure, and I'm going to put a half a cup of the hot water in, and I'm going to get the temperature for you right from the inside of my teapot. So it's reading 100 degrees, so the hot temperature is 100 degrees Celsius. 100.0 actually it read. And I'm going to bring the teapot over now and put the same amount of water in. So let's tare this so we can get the actual mass of the water. Okay, ready, and go. Add the hot water to it. So the total is 110 grams of water. And let's put the thermometer in and put the lid on and see what temperature we wind up at. Stir it up. And it looks like our final temperature in this experiment is 53.3 degrees. Okay, so here's all the data for the experiment. And we got a final temperature of 53.3 degrees Celsius from the experiment. But what should that value of T final actually be? Okay, so let's go through the math. There's going to be a lot of algebra here, and try to follow along. Okay, so we know two things. We know from the conservation of energy that Q of the hot plus the Q of the cold has to equal 0. And we know that both of these have MCATs. So Q of the hot equals MC delta T of the hot, and the Q of the cold equals MC delta T of the cold. And I know that delta T equals T final minus T initial. Okay. All right, so let's plug these values in. I'm going to take this and plug it in for Q of the hot, and I'm going to take this and plug it in for Q of the cold. So I'm going to get M of the hot, C delta T the hot, plus M of the cold, C cold, delta T, the cold, has to equal 0. And then I'll just rearrange this, bring 1 over to the other side. M of the hot, C delta T of the hot equals negative mass of the cold, C of the cold, and delta T of the cold. Well, since I was using water, the heat capacities cancel out. The masses were different, so I have to account for that, and I'm going to wind up with mass of the hot, and our delta T is T final minus T initial, and this is of the hot, and that's going to equal minus of the cold, T final minus T initial of the cold. Okay, and now what we need to do is combine like terms and solve for T final. I'm going to let you take a shot at the algebra, and we'll see how it goes. I'll do the rearranging of everything in a second, but give it a shot yourself, see if you could do it. All right, so we have where we left off was M of the hot T final minus T initial of the hot equals negative M cold T final minus T initial of the cold. All right, so let's do some algebra. I want to bring the M of the cold over first. So, and multiply it through. So I'm going to have M of the hot over M of the cold times T final minus M of the hot over M of the cold times T initial hot. And I still have n on this side, and distribute that through, so I'm going to get negative T of the final plus T of the cold. All right, so hopefully you followed along with that algebra. Now I'm going to start combining like terms. I'm going to bring the T finals over to one side. So M of the hot, M of the cold, T final plus T final from the other side. And I'm going to get T initial cold. And when I bring this term over, it's going to become positive M of the hot, M of the cold, T initial of the hot. Okay, and putting the numbers in, I'm going to give you a second, see if you can do that, and solve for T final. Okay, let's pop those numbers in. So we had 110 over 107 T final plus T final equals 14.1 degrees Celsius plus 110 for 107 times 100 degrees Celsius for the T hot. And when you crunch those numbers, you should get 2.03 T final equals 116.9 degrees Celsius, or T final equals 57.6 degrees Celsius, which is pretty close to the 53.3 that we got in our experiment. So try this at home, use different amounts of material, see if you can get close to the theoretical value in an experiment of yours, and share your results with me.